go ahead, share your screen. And just you can start whenever you're ready.
Can you see me? Can you see the screen?
Yeah, it looks great. Yeah, it looks great.
All right. Well, first of all, thank you very much for inviting me to give this presentation. And as always, I'm very sorry not to be able to be there in person. But anyway, that's where we are. Okay, so I'm going to talk about topological routes to new classical spin liquids. And this is work together with Owen Benton here in Dresden. And there's a preprint, which I'm mentioning here. Okay, so what is a classical spin liquid? So basically, it's a low temperature, high entropy state of, I'm going to be thinking about exclusively classical Heisenberg models. And the basic idea is that the system explores many low energy configurations, which are defined by local constraint. And I'm going to go into the local constraint in a lot of detail. But basically, you should think of this not necessarily like in a quantum spin liquid where you have a unique up to topological order ground state, but where you basically have a huge entropy left down to the lowest temperatures. And then you ask, what are the correlations encoded in this kind of system? And perhaps the best known such constraint you may have come across in the context of spin ice, where for spins on the Octa-Claw lattice, 2 spins point into each tetrahedron and 2 point out. Okay, so now let's go to Heisenberg models. So a generic Hamiltonian just has Heisenberg interactions between spins I and j. And you can often rewrite this as simple constraints so that you basically say for each simplex, say here, cluster may be a triangle or a tetrahedron, the total spin has to vanish. So these are the famous Octa-Claw and Coulomb Heisenberg models, which have been studied for a few decades now. So this was the Coulomb, this is the Octa-Claw. Okay, and historically, one of the first spin liquids that was found was a Coulomb phase. So basically there you can map the local constraint that the total spin of each tetrahedron must vanish essentially onto an emergent magnetic field. So emergent gauge field, which has 0 divergence. And then just like in classical magnetostatics, that gives algebraic correlations in real space. And these show up at with the pinch points, which are shown in the bottom left-hand corner here, where encircled, where basically you have features in the Bria zone, which are non-analytic, but they're not singular like in a Bragg peak. And these pinch points are basically tell you that you've got a Coulomb phase. But there are also other ones, so it took quite a while to find some new ones. Here's the Ruby lattice, which has also already appeared in Ruben's talk today. So it turns out if you think about these tetrahedra arranged in a corner sharing way on the Coulomb lattice, you end up with a spin liquid which has only short range correlations. So in spin space, all correlations are broad. Oops. But there is fractionalization in the sense that if you dilute the system, you get fractional spins occurring as effective degrees of freedom. So this is different from a Coulomb phase. And then the question is, how many such classical spin liquids do we actually know? And if you want to take your cue from quantum spin liquids, you may expect that there may be rather a lot. So here's a seminal paper by Mike Hermele, who found that for a square space group, enforcing a number of symmetries, they found 2 million Z2 spin liquids. And if you feel that perhaps you really need more because 2 to the 20 isn't a particularly big number, they did add the observation that this classification is not complete since they've done assumed some things which don't have to be true. Okay, so the question for today then, are there different kinds of classical spin liquids? Which ones are there? How do we systematically distinguish between them? And are there transitions between different kinds? And so we'd like to have some classification which is, in a very loose sense, topological. That is to say, a property which is insensitive to some continuous deformations, which I'm going to define for the specific purpose in a second. So continuous deformation, we basically mean that we continuously modify the ground state constraints, but without adding additional ones, and just ask as we change parameters in those, what do we get distinguishable spin liquids appearing. So for instance, we could have a particular constraint on a single cluster, and then we could change this by not, say, having all the spins summing up to 0 for each tetrahedron, but of having some linear combinations of the spins add up to 0. And then you can also add further neighbors and so on. And this is what's going to be the main part of the next few slides. So in particular, if you've got the honeycomb lattice, you can say, well, I demand that for each cell of the honeycomb lattice, the total spin has to be 0. I can extend this and say, well, I'm going to demand that the sum of all the spins on each honeycomb and the additional spins radiating out, as shown in red here, with a different coefficient, those have to add up to 0. And then you can ask, do you actually get different classical spin liquids in the process? Okay, so here's the main idea. So we have these local constraints in real space as properties of clusters that the spins on these clusters have to satisfy if you want to be in a ground state. And then you Fourier transform this. So you go to reciprocal space. And then, so the Fourier transform of the spin is just S of Q. If you've got n sides of the bases of your lattice, then you have n different fields, S of Q. So for Kagome, n is 4, for the Pyroclaw, n is 3, for the Pyroclaw, n is 4. And then all the action takes place in these L variables which encode what these constraints are. So they're basically the Fourier transform version of the constraint equation. The top box defines the constraint field L in the bottom. Okay, so this is an n component vector then, which encodes the constraint. There's one such field for each constraint in the unit cell. And so, for instance, in the Kagome lattice, you've got 2 constraints in each unit cell because you've got one up triangle and one down triangle in each unit cell. And now the point is that this vector field L, which is defined on in the Brillouin zone, can have a topological structure which is familiar from other places, like it can have vortices in 2D or skyrmion number in 3D. And so what I'm going to argue is that this topology of these constraint fields L can be characteristic of a particular classical spin liquid, and it can be insensitive to small changes in the constraint. So here's an example. Look at the honeycomb algebraic spin liquid. So this is a classical spin liquid, just defined as I mentioned earlier. You take each honeycomb, add the 6 spins and demand that they have to add up to 0. And this is going to give you the classical Coulomb spin liquid with pinch points that is shown here on the structure factor is shown on the right, bottom right-hand plot here. Okay, so now we have one constraint per unit cell. So one field L of Q. We have 2 sites per unit cell, so that L of Q is 2 components, as shown in the previous slide. And we have inversion symmetry, so that L is L has the following simple form, so that the 2 entries are complex conjugates of each other, so that you can write L as a point on the unit circle. Point in the unit circle then allows vortices with integer charge, just like in an XY model. So we can basically classify the spin liquids by how many vortices of which type it has. So to look at this in more detail, so we have on the left the plot of the constraint field in the Brillouin zone, shown as arrows. On the middle, there's the vorticity on the gamma and gamma prime points, oppositely charged vortices. And then the pinch points, which show you that there are these algebraic correlations, also live on the gamma and gamma prime, on the K and K prime point, and those coincide with the vortices. Okay, and now we change the constraints by adding these further neighbor interactions. So by adding these red points to the constraint, and then we can see what happens. So first, as you increase the gamma, which appears in the constraint, nothing happens. So you just change things around a little bit, but the vortex structure remains the same. Then when gamma reaches a third, pairs of vortices actually nucleate in the middle of the Brillouin zone boundary, so at the endpoints. So this is, in that sense, a topological transition. And then as you go further away, these nucleated vortex-anti-vortex pairs separate, and then you end up with a spin liquid which has 8 vortices in the Brillouin zone. So this is topologically distinct. And then the vortices which are moving along the edge of the Brillouin zone finally meet the corners. And so gamma equals a half, they merge, and then you get higher charge vortices at the zone corners. And this is basically now a rank 2 Coulomb phase. So where you no longer see a pinch point, which looks like a butterfly, but actually now a pinch point, which looks more like a Maltese cross with 4 bright and 4 dark directions rather than the butterfly with 2 bright and 2 dark directions. So this is then a transition to another classical spin liquid, which also has 8 vortices for each Brillouin zone. So this is then yet a different one. So here's an example for where we've explicitly given a prescription for how to change the constraints and how to go between different types of classical spin liquids. And here is a sort of phase diagram as a function of gamma, what kind of situations you can encounter. You can do the same thing in 3D. It's pretty much the same story. So here we're looking at the so-called Octa-Claw Lattice, so where the spins live on the bonds of a cubic lattice. So cubic lattice has X, Y, and Z bonds. That means there are 3 sides per unit cell. So and we have a nearest net. So we have basically, like before, we have interactions on a single octagon, and then one further neighbor and 2 further neighbors in blue and green. You can do exactly the same thing. You now have 3 components. You can look at how many constraints there are. You can define a skyrmion number, and then in the space of alpha and beta coefficients, which I showed you earlier, you can then get different skyrmion distributions throughout the Brillouin zone. So the details of that are a bit hard to digest in real time, but if you basically move along one of the lines here, you see how the structure factor changes and how you get these pinch points, and in particular, how again you get these multifold pinch points at transitions between different topological spin liquids, so that naturally you essentially end up with higher rank Coulomb liquids as transitions between lower rank Coulomb liquids. Okay, so let me skip this and summarize. Classical spin liquids can be classified by topological invariance related to the Fourier transform of their ground state constraints. So we've given some examples of this for the honeycomb and for the cubic lattice. The classification turns out to cover both algebraic and short range correlated spin liquids. So I didn't explain that in any detail. The phase transitions between those spin liquids can occur by the creation and annihilation of topological defects in Q space. And higher rank Coulomb phases with multifold pinch points can occur at phase boundaries between distinct lower rank Coulomb phases. So thanks a lot for your attention.
Awesome. Thank you, Roderich. Last speaker for